Hello, my dear students. Please subscribe our YouTube channel for more free video lectures and click on bell button for notifications and visit our website to purchase full course.
Welcome back to another session of Strength of Materials. In this session, we are going to start second chapter. In second chapter, there are two parts. First part is complex stresses and strains. Second part is stability of columns. In first part, we are going to deal complex stresses and strains. In second part, we are going to deal stability of columns. As far as gate is concerned, both these parts are important, ma'am. Generally, a question is coming from complex stresses and strains. Another question is coming from columns. So, you can expect 2 to 3 marks from this chapter, right? Right, for both mechanical and civil. If you are extra lucky, you may get extra question. Maybe sometimes 4 questions also, man. I have seen some gate papers. In those gate papers, even 4 questions came, 4 marks came from this chapter. So first we are going to deal complex stresses and strains, and second chapter is stability of course, second part of this chapter is stability of columns, right? First I deal complex stresses and strains, okay? So here I am writing 4 equations. First is sigma d is equal to P by A, and second tau is equal to F by AS, and third is equal to maybe sigma B is equal to M by Z, and fourth tau S is equal to T by J bar. So here I wrote 4 equations. These 4 equations are referred as elementary equations. Elementary equations of course, elementary equations are fundamental equations. Fundamental equations of structural engineering. Structural engineering, right? These 4 equations are referred as elementary equations or fundamental equations of structural engineering. So please copy these 4. I hope you copied. So let us examine what are these 4 equations. These 4 basic equations are dealing 4 basic types of loads. Loads are only 4 types: normal force, shear force, bending moment, and twisting moment. You may have different kinds of subcategories, but basically we have only 4 kinds of loads: normal force, shear force, bending moment, and twisting moment. These 4 fundamental equations are dealing the 4 basic loads, namely normal force, shear force, bending moment, and twisting moment. So these 4 formulae are giving response of the 4 basic loads. For example, if you apply a normal force, what stress will induce? How much stress will induce? If you apply shear force, what stress will induce? How much it will induce? Similarly, if you apply bending moment, what stress will induce? How much stress will induce? Similarly, if you apply twisting moment, what stress will induce? How much stress will induce? All these things, these four basic equations are giving. They are dealing four basic types of loads and their response. If you apply a particular load, what will happen to that structure? What stress may induce? How much stress may induce? Right? Let us try to examine these four formulae critically, right? What first formula says? If any structure carries normal force of P, a direct normal stress of P by A will induce or sigma D will induce. If any structure carries normal force of P, a direct normal stress of sigma D will induce, which is given by P by A. What second formula is saying? If any structure carries shear force of F, a simple shear stress of F by AS will induce or tau will induce. Similarly, if any structure carries bending moment of M, a maximum bending stress of M by Z will induce or sigma B will induce. If any structure carries twisting moment, a maximum torsional shear stress of T by J bar will induce. Like that man, right? These four basic formulae are giving response of the four basic loads. Let us examine further. In first formula, what is A? Area of cross section. In second formula, what is AS? Surface area. In third equation, what is Z? Section modulus. Section modulus of what? Section modulus of cross section of the beam. Section modulus of cross section of the beam. What is J bar here? Polar modulus. Polar modulus of what? Polar modulus of cross section of the shaft. Polar modulus of, this Z and J bar are special. Z is section modulus of cross section of beam. J bar is polar modulus of cross section of shaft. On the whole, first formula, third formula, fourth formula. 1, 3, 4 are giving stress on cross section. First formula, third formula, fourth formula are giving stress on cross section or cross sectional plane. Second formula is giving stress on surface plane. On the whole, these four fundamental equations are giving state of stress on only two planes, either cross sectional plane or surface plane. They are indicating state of stress on either cross sectional plane or surface plane. 1, 3, 4 are giving stress on cross sectional plane. Second is giving stress on surface plane. On the whole, only two planes they are dealing. Now, if I design any structure on the basis of these four formulae, my structure will be safe or unsafe. By using these four formulae, I design one structure, man. That structure could be any structure, maybe beam or shaft or anything, man. Okay? I design a structure on the basis of these four formulae. My structure will be safe or unsafe. There is no guarantee, man. There is no guarantee. If you design any structure by using these four formulae, indirectly, unknowingly, you are making one assumption. What is that assumption? In case of failure, failure occurs about either cross-sectional plane or surface plane, because these four formulae are giving stress on only cross-section and surface. So, if you design any structure by using this formulae, you are making one unknowing, assumption, man. What is that assumption? In case of failure, structure may fail about either cross-sectional plane or surface plane. But in actual practice, a structure may fail about any plane. Always, all structures need not fail about only cross-sectional plane or surface plane. A structure may fail about 45 degrees plane or 60 degrees plane or 22.5 degrees plane or 15 degrees plane. According to type of material, type of loading, combination of loading, a structure may fail about any plane. We don't know, man, which plane. But one point, always all structures will not fail about only cross-section and surface planes. They can fail about any plane. Any plane means whichever plane carries highest stress, about that plane failure occurs. That failure plane or critical plane need not be always cross-sectional plane and surface plane. Sometimes, failure plane will match with cross-sectional plane. Sometimes failure plane or critical plane matches with surface plane. But not always. Always failure plane need not match with cross-sectional plane and surface plane. Failure plane may orient about any plane. Critical plane may orient by any angle, man, we don't know. It is function of type of material, combination of load, amount of load, etc., etc. So what I am trying to say? What I am trying to say? I am trying to say it is not enough to find stress on only two planes, cross-section and surface. You should know how to find state of stress on all planes, man. Only two planes is not enough. These four formulae are giving stress on only two planes, cross-section and surface. This is not enough. You should know how to find state of stress on every plane. You should know how to explore state of stress on every plane. Then you can identify which plane is carrying highest stress, which plane is carrying lowest stress, etc., etc. Understand? Right. This is not enough. That is one point. Second point, these four formulae are giving individual effects or resultant effect. A structure is there. That structure is carrying multiple loads. A normal force is acting. A shear force is acting. A bending moment is also acting. Maybe a twisting moment is also acting. All loads are acting on the structure. When a structure carries multiple loads, individual effect is important or resultant effect is important? Which is more important? These four formulae are giving individual effect. We require individual effects or resultant effect. If structure carries only one load, these formulae are okay. If structure carries multiple loads, individual effect is not important. Resultant effect or overall effect is more important. That means you should know how to find resultant response or resultant effect of structure when it carries multiple loads. We should know how to find resultant effect on structure when structure carries multiple loads. This is second point, ma'am. First point, we should know how to find state of stress on every plane because it is not enough to find stress on only cross section and surface. Second point, we should know how to find resultant effect or resultant response of structure when structure carries multiple loads. Okay? In my BTech, I don't know this. Our faculty came, he started deriving a formula, he derived it, he derived 2-3 formulae, he started doing problems. Then again, he derived formula for major principal stress, he derived formula for minor principal stress, then again some problems. He derived how to find maximum shear, he derived formula to find angle of shear planes, then again problems. We don't know, man. We don't know why we are doing all those things. We didn't know. Why we are finding principal stresses, why we are finding maximum shear, why we were finding shear plane, why we were finding principal planes angles, etc. We don't know, man. Without knowing, simply we followed our faculty. We got good marks, of course, right? We got good marks. But at the beginning of every chapter, especially in BTech colleges, the faculty has to specify what things we are going to study, why we have to study, how we can use those topics, how we can use that knowledge in outside world, in what industries, in what fields we may require that knowledge. In three levels, an engineering college faculty has to teach. But in gate class, we never follow these things, man. In gate class, our objective is to produce good gate ranks, good gate scores for you. That is only my objective. But in engineering colleges, the faculty has to specify what things we are going to study, why we have to study, how we can use this knowledge in outside world, or in what fields, in what industries we may require this knowledge. So on three levels, the faculty has to teach. Okay, right. This is second man. And third reason. So here I am giving sample of reasons for studies of this topic, right? For studying this topic. Third, most of the brittle structures fail because of normal stress. Most of the brittle structures fail because of normal stress. They are very weak against normal stress. They are strong against shear. They are weak against normal stress. So brittle structures fail because of normal stress. Okay? That means while you are designing a brittle structure, you should know or you should find what is maximum normal stress in the structure about a critical point. What is maximum normal stress? If that maximum normal stress is less than strength of the structure will not fail. If that maximum normal stress is approaching strength of the structure, then structure may fail at any moment of time. Okay? While designing brittle structures, you should know how to find the highest normal stress. If that highest normal stress is less than strength, no problem, man. If that highest normal stress is approaching strength of the structure, at any moment of time, the structure may fail. Right. The highest normal stress in structure about critical point is called major principal stress. Highest normal stress in structure is called major principal stress. Lowest normal stress in structure is called minor principal stress. Highest normal stress, major principal stress. Lowest normal stress, minor principal stress. There is a plane, man. That plane carries highest normal stress. That plane is called major principal plane. Don't write, man. I will dictate everything, right? Don't write anything. Just listen. One plane is there. That plane carries highest normal stress. That plane is called major principal plane. Major principal plane is the plane which carries highest normal stress. Another plane is there. Its name is minor principal plane. This plane carries lowest normal stress. Understand? Major principal plane carries highest normal stress or major principal stress. And minor principal plane carries lowest normal stress or minor principal stress. So one question here. Brittle structures fail about which plane? Brittle structures fail about which plane? Always cross-sectional plane, always surface plane, or always major principal plane? In brittle structures, highest normal stress comes on major principal plane. So always brittle structures fail about major principal plane. Always brittle structures fail about major principal plane. In coming sessions, in a way, I am going to prove also, man. I am going to prove also brittle structures fail about major principal plane. Okay. So while design of any brittle structure, two parameters are very important. I should say two parameters are very important while designing any brittle structure. One parameter, what is magnitude of major principal stress? Second, what is angle of major principal plane? What is magnitude of major principal stress and what is angle of major principal plane? These two parameters are very important. If major principal stress is less than strength, no problem, man. If major principal stress is approaching strength, then at any moment of time, structure may fail. Similarly, about which plane? Brittle structures fail. Brittle structures fail about major principal. Understand? While designing of any brittle structure, these two are important, man. What is magnitude of major principal stress? What is angle of major principal plane? And otherwise, I should say, you should know how to find major principal stress. You should know how to find minor principal stress. You should know how to find angle of major principal plane, angle of minor principal plane, especially while design of brittle structures. You should know how to find principal stresses. You should know how to find angle of principal planes. This is third reason, man. Fourth reason why we are studying this topic, right? Most of the ductile structures fail because of shear. Ductile structures fail because of shear. They are very weak against shear. They are very strong against normal stress. So ductile structures fail because of shear. What shear? Highest shear. That means while design of any ductile structures, you should know how to find what is maximum shear. And a plane is there. That plane carries this maximum shear. That plane is called shear plane. Okay? So ductile structures fail because of shear above shear plane. That means while design of any ductile structures, you should know two parameters, man. You should know how to find two parameters. Number one, what is maximum shear stress in structure? What is maximum shear stress in structure? And what is angle of shear plane? What is angle of shear plane? Ductile structures fail about shear plane. Brittle structures fail about principal plane, major principal plane. All these things we should know how to find. Otherwise, you cannot design any structure, man. Simply, if you follow the formula, there is no guarantee of safety. Okay? If you design your structures on the basis of major principal stress and maximum shear, your designs will be more safe. Now a question may come. Why we have to find angle of major principal plane and angle of shear plane? Why we have to find angle of major principal plane and what is angle of shear plane? I already told, brittle structures fail about major principal plane and ductile structures fail about shear plane. So first you use some formula, find what is angle of major principal plane in a structure. Then, if at all any failure comes in that brittle structure, that failure should come about major principal plane. If major principal plane is safe, if nothing is happening about major principal plane, nothing is going to happen about entire structure. In brittle structures, if major principal plane is safe, nothing is going to happen to entire structure. Blindly you should not worry about every plane, man. You identify angle of major principal plane and always monitor that particular plane. Observe that plane. If nothing is happening about that plane, nothing is going to happen about entire structure. Similarly, in ductile structures, our ductile structures fail about shear plane. If I know angle of shear plane, I could observe that plane. If nothing is happening about that plane, nothing will happen to entire structure. If shear plane is safe in ductile structures, entire structure will be safe. Blindly we need not worry about every plane. Just observe those critical planes. In brittle structures, critical plane is major principal plane. In ductile structures, critical plane is shear plane. Observe only these two planes, man. If nothing is happening about these two planes, Nothing will happen about entire structure. If these two planes are safe, the entire structure will be safe. If at all any crack forms, that crack will form about either this major principal plane or shear plane. Like that, we should know how to do all these things, man, primarily for design purpose. All these concepts are useful in design of machine elements and design of structures, right? Either civil engineering or mechanical engineering, these concepts will be very helpful in practical point of view. In practical point of view. Understand? Because of all these reasons, we are dealing this particular chapter, man, right? We are learning various concepts on principal stresses, principal planes, shear stresses and shear planes. Okay? So I'm going to dictate few important points. All these points are very, very important. For our lifetime, try to remember all these points. Right? Never leave these points. Very important points. First point. Most of the brittle structures fail. First point. Most of the brittle structures fail. Most of the brittle structures fail because of normal stress. Most of the brittle structures fail because of normal stress. Previous IES question. Second point. Most of the ductile structures fail. Most of the ductile structures fail because of shear. Most of the ductile structures fail because of shear. Most of the ductile structures fail because of shear. Right. Then third point. Highest normal stress in structure is called highest normal stress in structure is called major principal stress. Highest normal stress in structure is called major principal stress. And lowest normal stress is called minor principal stress. And lowest normal stress is called minor principal stress. Next point. Fourth point. Brittle structures fail. Brittle structures fail. Brittle structures fail because of major principal stress. Because of major principal stress. Because of major principal stress about major principal plane. About major principal plane. About major principal plane. Next point. Major principal plane is the plane. Major principal plane is the plane. Major principal plane is the plane which carries. Major principal plane is the plane which carries highest normal stress. Highest normal stress. Highest normal stress or major principal stress. Or major principal stress. Major principal stress. Next point. Minor principal plane is the plane. Minor principal plane is the plane. Minor principal plane is the plane which carries minor principal stress. Minor principal plane is the plane which carries minor principal stress or lowest normal stress, or lowest normal stress, lowest normal stress. Next point. The angle between any two principal planes is 90 degrees. The angle between any two principal planes is the angle between any two principal planes is 90 degrees. Angle between any two principal planes is 90 degrees. In bracket you may write orthogonal. In bracket you may write orthogonal. Principal planes are orthogonal. Orthogonal means mutually perpendicular. Previous IAS question. Principal planes are orthogonal. They are mutually perpendicular. They are mutually perpendicular. Next point. I am going to give another definition of principal plane. Principal plane is the plane. Principal plane is the plane. Principal plane is the plane which doesn't carry any shear. Principal plane is the plane. Principal plane is the plane which doesn't carry any shear. Principal plane is the plane which doesn't carry any shear. Next point. What is the next point? I forgot. Please follow your serial number, right? Follow your serial number. Next point. Ductile structures fail. Ductile structures fail because of major principal shear stress, about shear plane, about shear plane. The major principal shear stress means highest shear stress in structure. Highest shear stress in structure is called major principal shear stress. Next point. Shear plane is the plane which carries highest shear. Shear plane is the plane which carries highest shear. Okay? Right. Next point. The angle between any two shear planes is The angle between any two shear planes is 90 degrees. The angle between any two shear planes is 90 degrees. In bracket you may write orthogonal. The angle between any two shear planes is 90. Shear planes are mutually perpendicular. Okay? Principal planes are mutually perpendicular. Shear planes also mutually perpendicular. Next point. The angle between a principal plane and corresponding shear plane, angle between a principal plane and corresponding shear plane is 45 degrees. 45, angle between a principal plane and corresponding shear plane is 45 degrees. Angle between any two principal planes, 90. Angle between any two shear planes, 90. Angle between a principal plane and shear plane is 45 degrees. Of course, we are going to prove everything, man, right? Next point. Von Mises stress is given by Von Mises stress is given by 1 by square root of 2 into square root of sigma 1 minus sigma 2 minus sigma square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. Von Mises stress can be calculated by using this formula. Please copy this formula. Von Mises stress is given by 1 by square root of 2 into sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. Here sigma 1, sigma 2, sigma 3 are principal stresses. Sigma 1 comma sigma 2 and sigma 3 principal stresses. Especially mechanical students, try to remember this formula, right? I will explain later, right? Next point. Ductile machine elements are designed. Ductile machine elements are designed on the basis of Von Mises stress. On the basis of Von Mises stress. Few minutes back I told ductile structures fail because of shear. Right now I am saying you have to design ductile structures by using Von Mises stress. Am I giving two contradictory statements, man? Am I giving any contradictory statements? Absolutely no. They are same, man. See, sigma 1 minus sigma 2 gives a shear. Sigma 2 minus sigma 3 gives another shear. Sigma 3 minus sigma 1 gives another shear. Actually, this is one shear, second, third, three shears, man. Von Mises stress is a kind of resultant shear stress. Von Mises stress is a kind of resultant shear stress. So, I am not giving contradictory statements. I am giving almost same statements, man. Okay? Right. Why we are designing machine elements on the basis of Von Mises stress? What is speciality of Von Mises stress? Mechanical people may know it. Civil people may touch this topic in theories of failures. In theories of failures, maximum distortion energy theory is there. At the end of that entire theory and derivation, we got this formula, man. This formula is outcome of maximum distortion energy theory. Only that point civil students may know, but mechanical people may know more than that, man, right? What is importance of this Von Mises stress? What is importance of the Von Mises stress? Think about it. If you open any analysis softwares like ANSYS, Nastran, Edina, CAFM, like that, you will find one option. In every analysis, you will find one option. Von Mises stress option. By clicking on Von Mises stress, the software gives Von Mises stress at various points of structure. Why we need this stress? Why it is important for ductile machine elements? Practically in outside world, ductile machine elements are designed on the basis of Von Mises stress, not any other stress, man. This is the most important stress in design of ductile machine elements. Okay, why it is important? Okay. I want to manufacture a car and I want to sell my car in outside market. Being designer, I may design all the components on paper. Directly can I go to production, man? I cannot go. Before going after production, first we have to prepare some models and we have to run number of tests on those models. Upon satisfactory results of all those tests, finally we may fix all the materials, dimension, shape, size, etc., etc. Then finally we may manufacture a car and we may start selling cars in market. But before that, we have to run number of tests. Tests are two types: destructive tests, non-destructive tests. With non-destructive tests like gamma ray analysis, X-ray analysis, ultrasonic, dye penetrant test, etc., etc., no problem, man. We are not going to lose our components or assemblies. But in destructive testing, we may lose our product, man. For example, on every car, the car manufacturer has to run number of tests. One of the tests is crash test. Crash test. If a car is crashed against another car with certain velocity, what will happen to car? If our car is crashed against a bus or lorry, what will happen to our car? Or if our car is crashed against a roadside tree or roadside wall, what will happen? Crash test. We have to run crash test. What will happen to car? What will happen to driver? Right? We have to run a test like this, man. While conducting this crash test, we may measure several parameters, man, right? One of the parameters is the actual failure stress, actual fracture stress. In actual condition, at what stress a component is breaking. Not in laboratory, man, not in theory books. In actual loading condition, at what stress a component may fail. By conducting crash test, we may find it. Similarly, drop test. If a car drops from a bridge into river, what will happen? If a car falls from a hilly road into valley, what will happen? Drop test. In all these tests, we find actual failure stress of machine elements. Okay? Conducting crash test or drop test are not easy. They are very expensive. After conduction of crash test, can I get back my car, man? Our car is rammed against a lorry, man. After crashing, can I get back my car? My car may become a lump of metal. I may permanently lose my car. So, crash testing, drop testing, all these are very expensive. They may require experts. They may require a lot of time, lot of preparation. We may require sophisticated instruments, etc., etc. At the end, we find one parameter. That parameter is actual failure stress. But surprisingly, for few popular ductile materials, the actual failure stress matches with von Mises stress, man. The actual failure stress matches with von Mises stress. Almost they are equal, man. If my von Mises stress is giving actual failure stress, why I have to conduct so many tests, man? We need not conduct so many tests. For practical validation, we may conduct 3-4 tests. Then we may validate with von Mises stress. This is really very important stress. This von Mises stress may matches with actual failure stress for many ductile materials. For brittle materials, they don't match. Okay, because of all these reasons, we are studying this topic. Of course, to find von Mises stress, you should know how to find sigma 1, sigma 2, sigma 3. Unless you know how to find sigma 1, sigma 2, sigma 3, you cannot find von Mises stress. So because of all these reasons, we are dealing this chapter, man, right? Okay, in this session, I have given few outlines or basics of this chapter. In coming session, I am going to derive some formula and we start doing some problems. Until next session, have a good day. Thank you.